This framework of hypothesis testing, of choosing a null hypothesis and then seeing whether our data is consistent with that hypothesis, is often useful. However, it's a little bit limiting because I don't necessarily care that much about whether my data contradicts one particular value. What I'm more interested in is which values in general my data contradicts or does not contradict. So the idea of a confidence interval is that we can come up with a range of values that, if they were the null, would not be contradicted by our data. So if I'm doing a test for the null hypothesis that the population mean of women's heights is 65 inches, I'm either going to reject that null hypothesis or not based on the data. Right? My p-value will either be less than whatever the cutoff is, for example, 0.05, or more than that cutoff. I'll either reject that or not. And suppose that, as in the data set we were imagining earlier, I do reject this. So 65 is rejected. So I'll write over here, not 65. Okay, we don't think mu is equal to 65. Great. But what if I had done that entire test for the null hypothesis that mu is equal to 60? And we see whether my data contradicts that. Okay? We would also get a p-value. And perhaps we'd find that we'd also reject that. Okay, fine. But we could also do the whole test where we assume this was equal to, I don't know, 64.3. And perhaps that value is not contradicted by the data, so it may be the right answer. It may be mu. I could have done that test for any particular null hypothesis value. And there's a certain range of values, probably values close to the sample mean I actually obtained, that would not be contradicted by the data. Again, the set of null hypotheses that would not be contradicted by the data are going to be the values close to the mean that I actually observed. So this range of values is called a confidence interval. And here's the way I like to think about it. We've been saying that the probability that this value y falls within -2 and 2 standard deviations of its mean is 0.95. Right? We've been saying that based on the central limit theorem. So whatever mu is minus 2 times sigma over radical n, whatever mu is plus 2 times sigma over radical n. Okay? But for the purposes of talking about this confidence interval, let's admit that we never really know. Sigma, let's put an s here instead. Okay? This should still be approximately true. Technically, in terms of this 2, we should use something that is more appropriate for a t-distribution, but if your sample size is big, it does not matter. This 2 is fine. Okay. So here we go. I'm going to try to use this quantity here to come up with an interval for mu. What are the values that would not be contradicted by the data? So if the probability that y bar, if I repeatedly sample from a population with mean mu and variance sigma squared, the probability that y bar is in this range is 0.95, that's the same as saying that this inequality would hold if I subtracted mu here, here, and here. Right? I should be able to do that. Okay, so I'm going to subtract mu. Okay, I'm just manipulating the inequality. This inequality is also true if this one's true, so it's true with probability 0.95. Okay, now what I'm going to do is subtract y bar from here, here, and here, which I can do because that will still make the inequality true. So I'm going to subtract y bar. I erased it in order to subtract it there, and I'm going to subtract it here. Okay? All right. And now what I'm going to do is I'm going to multiply each part of this inequality by -1. What happens when we multiply each part of an inequality by -1? The signs flip. The signs flip. The inequalities flip. So I've got y bar plus 2s over radical n is greater than mu is greater than y bar minus 2s over radical n with probability 0.95. So the way to think about a confidence interval is that we're sampling from a population that has some fixed mean and some particular variance. And the probability that y bar will fall in a certain range is 0.95. But that's the same as saying the probability that y bar plus or minus 2 s over radical n will actually contain the true mean is 0.95. The probability that this interval, these upper and lower bounds, contain that mean, that that population mean is between these two values, is 0.95. And the way to think about this is as follows. Here's the actual population mean, okay? And I'm going to sample from the data. And perhaps the y bar I get is right there. It's not exactly equal to the population mean, but it's close. And here's my interval. Here's y bar minus 2s over radical n. Here's y bar plus. In this case, as I've just drawn this, y bar falls within that range. Perhaps I draw another sample from the population. Here's y bar. Here's my interval. Again, my interval includes mu. But now here's a sample that's particularly unusual. Y bar is kind of low, and the interval doesn't quite include mu. The idea is that the confidence intervals are constructed by calculating this lower bound and calculating this upper bound such that there's a 95% probability that the interval will cover the true value. And if we did this by simulation, what you'd see is that 95% of samples would lead to intervals that do indeed cover that true value. We need to generalize this only slightly if we're going to be thinking about two samples. The idea is that the probability that x bar minus y bar falls within a certain range is 0.95. What is that range? Well, it's the difference in population means minus 2 times the square root of sx over nx plus sy over ny. And the difference in population means plus 2 times the square root of sx over nx plus sy over ny. If I wanted to assume that the variances were the same in the two populations, I could just substitute sp squared for each of those two quantities, and that would work as well. Okay? But if I go through the same steps I had before, I can show that this inequality can also be written x bar minus y bar minus 2 times sx squared over nx plus sy squared over ny is less than mu x minus mu y is less than x bar minus y bar plus 2 times the square root of sx squared over nx plus sy squared over ny. The probability of that is 0.95. In other words, if you sample from two different populations and calculate the mean in each of those, the sample mean in each of those two samples, the difference in the sample means that you obtain has a 95% chance of falling in this range. That's the same as saying that if I use my data to calculate this lower bound and I use my data to calculate this upper bound, the probability that the true difference in population means falls within that range is 95%.